In order to discuss Newton's second law of motion, we need to introduce the concept of force in dynamics. According to the first law, the acceleration of a body is a manifestation of some effect of other bodies. If the velocity of a body is changing, that is if the body is accelerating, it is always the consequence of an effect of other bodies on the moving body. In this example, the moving ball A collides with the ball B. As the result of the collision, the ball A changes its speed and the direction of its motion, that is the ball B had an effect on the motion of the ball A. In the description of the collision, the moving bodies are approximated with the point masses A and B, and their velocities are measured in an inertial frame. If a body has such an effect on another body, that changes its velocity, then we call this effect a force acting on the accelerating body. Then force is a physical quantity, measuring the effect of bodies on a given body, which changes its state of the motion. The change in its state of the motion means the change of the velocity of the body, that is the change in its speed or the direction of its motion. Let us consider a moving body. If other bodies has an effect on this body which accelerates its motion, then instead of this effect, we talk about a force acting on the body which accelerates it. That is, we represent the concept of the effect between bodies with a physical quantity, namely the force exerted by and acting on bodies. The concept of force is historically connected to the force exerted by muscles, since it is the most obvious type of force which is able to accelerate bodies. In dynamics, force gained a general meaning, since arbitrary objects or physical processes can produce effects causing acceleration in the motion of a body. It is important to understand this generalization of the concept of force, since we can find forces of different nature in the everyday life. We have already mentioned mechanical force. A typical example for application of mechanical force is the traveling carriage drawn by horses. Beside mechanical force, we present examples for other types of force. The freely falling or thrown bodies are subjected to the gravity of the earth, and their acceleration is due to gravitational force. Suspension springs applied in vehicles can compensate uneven road surfaces, since the elastic force exerted by them is able to absorb shocks. The decrease in the velocity of a body thrust on a plane surface, or the fact that a matchstick can lit by rubbing it against the rough side of a matchbox, can be attributed to the frictional force between surfaces. Based on the first law and these examples presented above, we can conclude that if a body is accelerating, then a force is acting on it. Therefore, we must assume that there is a relationship between the force acting on a body and its acceleration, which allows us to measure the force. Let us consider a ball made of wood, which is moving at the velocity v0 or at rest on a flat surface. If the ball is at rest, then v0 is 0. We can push the ball, giving it a greater the velocity v1. Then we measure the distance s1 covered by the moving ball in the time interval t, which is equal to v1 times t. If the time interval t is short enough, then we obtain the average acceleration a1 of the ball by computing the ratio of the difference between v1 and the initial velocity v0 to the duration t. This average acceleration is associated with the mechanical force we applied to the ball when we pushed it. If we apply more force when we push the wooden ball, then the ball will travel with the speed v2, which is greater than v1. That can be demonstrated by measuring the distance s2 covered by the moving ball in the time interval t. The distance s2 is equal to v2 times t, and it is greater than s1. As a result, the average acceleration a2, which is equal to v2 minus v0 divided by t, is also greater than the acceleration a1 obtained in the first case. Therefore, this experiment shows the following relationship between force and acceleration. The greater the force that is applied to the ball, the more the ball will accelerate. We can also associate the direction of the force acting on the ball with the direction of its acceleration. If we study the relationship between acceleration and force, then we can also determine the relationship between acceleration and inertia, and introduce the concept of mass. We have seen in the experiment with the wooden ball moving with the initial velocity v0, if we apply a given force to the ball, then it will travel the distance s1 in the time interval t. From the measured distance and time we can determine its velocity v1 given by the ratio of s1 to t, and its average acceleration a1, given v1 minus v0 divided by t. We can repeat this experiment with an iron ball of the same size as that of the wooden ball. If we apply the same force to the iron ball as in the case of the wooden ball, then the iron ball will travel a smaller distance s2 in the time interval t than the distance covered by the wooden ball. The velocity v2 of the iron ball is given by s2 divided by t, and it is less than the velocity v1. As a result, the average acceleration a2, given by the ratio of v2 minus v0 to t is also smaller than the average acceleration a1 of the wooden ball. Then we need to apply more force so that the iron ball could move with the same acceleration as the wooden ball. By virtue of the first law, we can say that the iron ball has greater inertia than the wooden ball does with the same size, as it resists more against the attempt to change its velocity than the wooden ball did. On one hand, this result of the experiments indicates that the greater the force is acting on a body, the greater the acceleration the moving body has. On the other hand, there must be a physical quantity expressing the measure of the inertia of the bodies, which determines the relationship between the force exerted on a body and its acceleration. We call this physical quantity the mass or the inertial mass of bodies. In the example shown above, inertia and mass are associated both with the wooden ball and the iron ball. We can interpret the result of this experiment as the demonstration of the difference of the masses of the two balls. The mass of the iron ball is greater than the one of the wooden ball. In this case we say that the iron ball is heavier than the wooden ball. In these experiments we compared the amount of the force applied to the balls when pushing them. For this comparison we need to determine the amount of force. However, instead of using our sensory perception of the force exerted by our muscle, we can apply a more accurate method to measure force. In the following experiment, we use simple harmonic motion to find the exact relationship between acceleration and force. If we can measure the acceleration of a body performing oscillating motion, then we can determine the exact amount of force acting on the oscillating body. In this experimental setup we suspend an iron cylinder to compensate its gravitational acceleration, and attach two springs to the body. Both the spring are fixed at their other end, as seen in the figure. If we orient the x-axis so that it is along the axes of the springs with the origin in the middle of the cylinder, then the cylinder is at rest at origin, and it can move to any position along the x-axis in both directions. If we move the cylinder to the position x0 and release it, then the body starts a harmonic oscillation with the maximum amplitude x0 and the period t due to the forces exerted by the springs. The angular frequency omega of the cylinder is equal to 2 pi divided by the period t. We already know the equations of motion of simple harmonic motion. The displacement x of the oscillating body is given by x0 times the sine of omega times t. Its derivative with respect to the time t is the velocity of the body, which is equal to x0 times omega times the cosine of omega times t. The time derivative of the velocity gives the acceleration of the body, which is given by minus x0 times omega squared the sine of omega times t. If the maximum amplitude x0 is given, and we measure the period t of the motion, then we can determine the acceleration of the iron cylinder at any given time t. We only want to determine the maximum acceleration at the turning point x0 of the motion, that is, when the time t is equal to the 1/4 of the period t. Since we can substitute the expression of the angular velocity omega into the equation of acceleration, we obtain 4 pi squared times x0 divided by the square of the period, times the sine of 2 pi squared times t divided by the period. Here it is enough to use the absolute value of the acceleration. Then the magnitude a0 of the acceleration of the cylinder at the turning point x0 is equal to 4 pi squared times x0 divided by the square of the period t. As we have already said, in order to determine the acceleration at that point, we only need to fix the maximum amplitude x0 and measure the period t or its square. Now we perform 3 experiments. We choose the maximum amplitude x0 of the cylinder to be 1 cm, 2 cm and 3 cm respectively, and measure the corresponding period of its oscillation. We find that the period is the same in each case. That is, t squared has the same value for each maximum amplitude x0. We can conclude that the acceleration is 2 times and 3 times greater in the second and the third cases than the one measured in the first experiment. Then we have demonstrated that the acceleration of the iron cylinder at the turning points is proportional to the maximum amplitude x0 of its oscillation. We know that the greater maximum amplitude we choose for the oscillation, the more we stretch or compress the springs. But we can also assume that the more we stretch or compress the springs, the more elastic force they exert on the cylinder. Based on these observations, we interpret the result of the experiment as follows. If we want to determine the forces accelerating the cylinder, we can make the simplest possible assumption on the relation between the force and the acceleration produced by the force. Let us say that the force F0 acts on the oscillating cylinder at the maximum amplitude of 1 cm with the acceleration a0. Then the force of 2 times F0 will act on the body, when it has the acceleration of 2 times a0 at the maximum amplitude of 2 cm. Similarly, the acceleration of 3 times a0 at the maximum amplitude of 3 cm is produced by the force of 3 times f0 acting on the body. Therefore, we assume that the force acting on the iron cylinder is proportional to the acceleration of the body. As a result, the force acting on the body at the maximum amplitude x0 of the oscillation is proportional to that maximum amplitude in this experiment setup. Now we replace the iron cylinder with a lead cylinder which has the same size, and measure the period t of oscillating body with the maximum amplitude of 1 cm. In this case, the force acting on the lead cylinder is still equal to f0, but we find that the square of the period t is 1.5 greater than the one measured for the iron cylinder. Then the acceleration of the lead cylinder at the maximum amplitude of its oscillation is equal to a0 divided by 1.5, or it is 2/3 times the acceleration measured for the iron cylinder. We use the iron cylinder again, but we attach another iron cylinder with the same size to it, and perform the same experiment with the maximum amplitude of 1 cm. Then the force acting on the cylinders is still equal to f0, but the square of the period t is 2 times greater than the one measured for one cylinder. As a result, the acceleration of the double iron cylinder is the half of the acceleration measured for the single one. We have seen that the same amount of force acts on the bodies in these experiments, since the elastic forces in the stretched and the compressed springs at the same maximum amplitude are the same. The experiments show that the same force can produce such accelerations of the lead and the double iron cylinders, which are 2/3 and the half of the acceleration measured in the original setup. This fact can simply be attributed that the masses of the lead and the double iron cylinders are 1.5 times and 2 times bigger than the mass of the original iron cylinder. Then we can conclude that the acceleration of a body is inversely proportional to its mass for a given force acting on it. In these experiments, we determine the relationships between the force acting on a body, the mass of the body, and the acceleration of its motion. Based on these findings, we can state Newton's second law in the following form. The acceleration of a body is proportional to the force acting on the body, inversely proportional to the mass of the body, and it takes place in the direction along which the force acts. Here we can see a point-like body or a point mass with the mass m. The horizontal red arrow represents the force F acting on the point mass, which produces the acceleration a of the moving body represented by the horizontal green arrow. Both the force F exerted on the body and the acceleration a of the body point in the same direction. By virtue of the second law of motion, if we apply 2 times greater force to the same point mass, then its acceleration is 2 times greater than it was in the original case. The second law also claims that, if the same amount of force is applied to a point-like body with a mass of 2 times m, then the acceleration of the more massive body is the half of the original one. These example demonstrates that the force is proportional to the product of the mass and the acceleration of the body. That is, the force F acting on a body is equal to some proportionality factor c, times the mass m of the body, times its acceleration a. We can also say that the acceleration of a body is equal to 1/c times the force F acting on the body, divided by the mass m of the body. The value of the proportionality factor depends on the choice of the unit of mass and force appearing in this equation. Since we have not fixed these units yet, we will choose such units which give that the proportionality factor c is equal to 1. Then, Newton's second law states that the force acting on a point mass is equal to the product of the mass and the acceleration of the point mass, that is, the force F is equal to the mass m times the acceleration a. We call this equation the fundamental equation of dynamics. We have seen that force introduced in the second law of motion has both magnitude and direction. Therefore, we represented forces with vectors, where the length of the vector gives the amount of the force acting on a body, and its direction points to the direction of the acceleration of the body produced by the force. However, the fact that force has magnitude and direction does not necessarily determine whether force is a vector or not. This question can only be answered by examining the superposition of more forces. We will see later that the force acting on a body is equal to the vector sum or the net force of all the forces acting on it. Based on this observation, we can say that force is a vector. This uncertainty might be surprising at first sight, since we would immediately conclude that force is a vector, based on the second law of motion. The law states that the force F acting on a body is equal to the mass m of the body times its acceleration a. In the right-hand side of this formula, the acceleration derived from the position vector is a vector. The mass m of the body is a scalar, and we expect if we multiply a vector with a scalar then we obtain another vector. Then we would say that the quantity F in the left-hand side is a vector, and the whole equation is a vector equation. However, It does not necessarily follow from this equation that force is a vector, since force is not the product of mass and acceleration, but such an effect of bodies which is measured by this product. The superposition of several different effects can only be examined in experiments, and only the results of these experiments can confirm that the vector sum of forces gives the correct description of such a superposition. In fact, this should not be surprising, since we have already seen that the nature of different kind of forces is rather heterogeneous. The only common feature in mechanical, gravitational, elastic and frictional forces is that each of them is a manifestation of some effect on bodies. And it is far from being obvious how these together produce a net effect on bodies. Since the kinematic quantities, like the velocity and the acceleration of a body, are derived from its position vector, they are vectors by definition. This is not the case for force. The second law of motion alone cannot guarantee that force is a vector. Rather, empirical evidence is required for the confirmation of this assumption.